So far, we have talked about coherence, or how we keep a single piece of data consistent in our system, or how we keep a single cache line consistent. We're going to expand that kind of reasoning uh, to cover all the different items we have in our memory. Sometimes these kind of concepts are best explained by an example. So let me show you an example, and it's actually a trick example. Let's see if you can hang on anyhow. So we're going to look at a very simple piece of code that sort of shows how you can do what's called flag synchronization between threads. So initially, the value of the variable global variable flag is 0, and the value for A is also 0. Then we have one thread executing to the left and one thread executing to the right. The left thread first sets the value of A to 1. Then it signals that A is valid by raising the flag, saying, hey, I raised the flag, so anybody can start consuming the value of A now. On the right-hand thread, we have a thread that has been waiting here forever to see the change of the flag happening. As soon as you see that the flag goes from a 0 to 1, it falls out of the infinite loop. It reads the value of A into a local variable and prints that value. So here it is, the dependence between these operations, that this executes before that, and this must execute before that, and these transactions here also execute in the order that I showed you. So the first trick question I'm going to ask you is, what value will get printed down here? And I can see three possible answers. One is that the value 0 will be printed. The other one is the value 1 will be printed. And the third answer is that this is undefined. And I told you it is a trick question. The true answer is it's undefined. And the reason it's undefined is that I have not told you what the memory model of the system where we execute this piece of code is. And if you don't know the memory model, you cannot answer this question. Because the memory model defines what assumptions we can make about different observation of value change orders that we can see in the system. Let's look at a slightly more complex problem. So this is a problem where we can test a property called causality or causal correctness. It has two variables, A and B, initially 0, has 3 threads. Left thread changes the value of A, middle thread waits for the value of A to change, after which it changes the value of B. And the right thread will wait for the value of B to change, after which it reads the value of A into local variable and it prints it. So here is what my intuition tells me, that this happened first. This statement here must have happened before this statement. Otherwise we wouldn't have seen the value change. And this statement happened before that statement because they're in program order. Then we have another dependence saying that this statement here must have happened before that statement. And then we have a third dependence saying that that statement over there must happen before this and that because they are in program order. Once more, I'm going to put the trick question. What value will get printed down here? And this time you may have been a little more alert since you knew it was a trick question. My intuition would have told me that 1 should be printed down here because the value here changed, A changed its value to 1 here, and that happened before we saw this statement executing. And we know from program order that this happened before that. Okay, so then you can draw the conclusion that A must have happened before B. At least that's the observation that this node over here. So the question is, just because a thread in the middle has seen that A happened before B, does that imply that this thread over here also must agree that A happened before B? So see clearly that B happens here. But the question is, can we be sure that it will agree that A happened before B? we're going to fix this. We're going to talk about memory models. We're going to talk about some models that will fix these kind of problems, and we're going to talk about other ways of programming integrated models so we actually can make this code execute correctly. First, we're going to look at one more example. And this is a little more tricky example to understand what's going on. It's a mutual exclusion algorithm that was introduced by Decker. And so the mutual exclusion is that we would like at most one of these two threads to get into the critical region or to declare success. So if left prints A1 or if the right prints B1, that's okay. But what is not an okay, it's also okay actually if none of them win, according to the definition of this algorithm. But what is not okay is if both we see that the left side prints A1 and we see the right side printing B1. So looking at this, trying to reason about the trick question here, so the way this algorithm works is that first the left side tries to make life miserable for the right side by setting the variable A to 1. Then it sees if B is still equal to 0, then it says is it 1. Likewise, the right side tries to make life miserable for the left side by setting B equals to 1. Because if it's B equals to 1, that we make the left side its test fail before it sees if A is still equal to 0. If so, it declares success. So clearly there could be a race here where we change the value of A and B exactly at the same time, and then these tests would both fail, which is okay. The question is it possible that both A and B wins? So here's the trick question, and I'm not even going to wait for you to click the boxes because by now I know I can't fool you anymore. You would probably all click the box undefined because this is also, of course, an undefined situation since we don't know what the memory model is. So let's start to talk about memory models. So what are memory models? So memory models or memory ordering is another synonym for that. Is sort of related to cache coherence. So cache coherence defines a per datum value change order, or says that there can be many copies of a piece of data but only one value. But it reasons about a specific piece of data. Memory model defines some kind of value change order for all the data in the system. So memory ordering defines the guaranteed memory ordering. That's the way I look at this as a hardware designer. It's sort of a contract between the hardware and the software people. So if we at Sun Microsystems agree that we're going to build a specific server with a specific memory model, then all the programmers know exactly what kind of code they could write and what kind of assumptions they could make about our memory model. And vice versa, we know if we only implement this model, hardware model, we know that all the software that ran on the previous generation servers would also run on this generation servers. But as you can see, these kind of memory models could sometimes get a little hairy. So it's even if you've been part of designing the previous server, it's not a super easy task to make sure that the next server has the same memory ordering properties. And as we already saw, if you don't know what the memory order is, there are many situations in the execution that you would want to be able to reason about. And actually, lots of executions that would be undefined. So how can you observe an order in software? Okay. So how can you answer the question, in which order did A and B change their values? So let's assume that the variable A gets a new value and the variable B gets a new value. The question is, which order did those value changes occur? First B or first A? Because typically there is some kind of order defined between them. Not always. So one way to define, to write a piece of software that could detect this would be a software that first reads the new value of A, after which it reads the old value of B. Then we can draw the conclusion that new A was born before new B was born. You can also determine which order A and B change the value by being the one to change the value of A and B. So if you are the one who performs a store operation, new B, and then a load, sorry, if you perform a store operation, new B, and then, and this slide is wrong here, so if you call it store operation, new A, after which you will perform a load operation, loading old B, then you know that A was changed first by yourself before B was changed, possibly by somebody else. We don't know, but at least we determined that old B was still alive after we changed the value of A. So new A is what it says here. And then finally, you can determine order by being that you yourself are the one who make the changes. So you write new A followed by writing new B, and of course you know new A happened before new B. So this is sort of value change ordering. You can also have a different ordering to rely on. That's the program order. So each thread has a sequence of instructions that is going to be executed defined by the programmer, and that sequence of instructions is called program order. So you can assume that those instructions are actually executed in that order. That's the other order we're going to rely on in the reason why these orderings. We're going to look at an example here. So we have two threads, reading, writing lots of different values. And here we denote A prime to be the modified value and the old value being A. So we're going to figure out now. So these instructions read and write old and new values in some kind of order, each one in their own sequence. So this is the program order for thread 1, and this is the program order for thread 2. Then we can look at the value order here and say that this happened before that. Why? Because here we loaded the old value of A, and here we stored the new value of A. So even though these execution took place in two different threads that may be sitting far, far away from each other, in looking at the value order, we can still determine that the one to the left happened before the one to the right. Likewise, you can see that store B prime happened before load B prime, because otherwise we couldn't load the new value over here. You can also see that load C happened before store C, because otherwise we would, due to value order, we would get the new value here, and so on. So we can go on and we can define the order between all these different transactions, and then we, on top of that, also have the program order for each thread. Now, after we made this observation, we can make some bold statement in which global order the instructions of thread 1 and the instructions of thread 2 executed. Simply by putting them together based on our observations, saying which happened before which, we can draw the conclusion that this is the order they were performed. We create some global order saying that load A happened before store A, happened before store B, happened before store load B, and so on. Just based on the value order, we now manage to interleave the instructions of two completely different threads together. But this is not the only possible order. This is one order. We could just as well have executed instructions in this order, because that is also true to the value order that we've seen. Because here we also have load A happening before store A. We have store B happening before load B, and so on. So there are lots of possible interleavings. They will all agree with the value observations that we saw. This is exactly the kind of semantics that you have in sequential consistency. So sequential consistency was the first memory model or memory order that was ever defined by Leslie Lamport, who has done many other things, like writing Lapesh and so on. And Leslie Lamport says that that sequential consistency is the global order you achieve by interleaving all memory access from all different threads. And the way I like to picture this myself is to say we have a shared memory here, we have all the threads down here, and then we have a switch. And the switch can choose one of these threads, and they can perform a load or a store from that thread. But it's going to be performing a load and a store at the time going to the shared memory. And that's, once more, the memory model that we all should agree on is implemented. We all know there's going to be lots of caches and so on sitting here. But if we would like to implement a sequentially consistent memory system, even though we have lots of caches sitting down here, we have to make sure that the ordering that the software can see is equal to the ordering it would be if you have this kind of pretty rudimentary kind of building a very well-ordered, coherent shared memory system. So as I said, the software should not be able to detect any contradictive orders at all. So if one thread over here managed to observe one order by some sequence of instruction, then no other thread should be able to observe the contradictive order. They don't have to observe exactly the same order. If this says A happened before B, some other one says B happened before C, then the thread here can say A happened before C. They are all agreeing with each other with respect to the global order. But if it was a thread here that say B happened before C, that's a contradiction that we don't tolerate here in the Leslie-Lamport sequential consistency. Also, when you have this kind of memory model, this is good because programmers' intuition is meeting. This is, in my mind, how I think that hardware should perform before people told me about memory models. However, this is very restrictive and it's hard to make a good implementation and often you have to leave some performance on the table to be able to achieve that. Okay, let's go back to our examples here. We have the flag synchronization. Okay, and the flag synchronization now executed under sequential consistency. Sequential consistency where all loads and stores performed by a CPU are put in some global order. Then I repeat the question again. So given sequential consistency, what value would be printed? So value 1 is printed here because this is the program order. Here's the value order. And we can make use of the value order and program order to order all these transactions in some global order. So this is one possible global order. And there is no contradictive global orders, which means that this statement x equals A is happening after A equals 1. So that means that x should get the value 1 and we should print the 1. How about this? The causal correctness problem. Once more, assume here that we have sequential consistency and we have this kind of order. And I put the question, given sequential consistency, what value will be printed? So once more, we print the value 1. So why is that? Well, because sequential consistency says that there is a global order that cannot contradict the order you get if you take the value order and the program order. So this order here that we get by following the red line, that order is one possible interleaving of all the different loads and stores happening in this machine, but nobody should be able to contradict that order. So we know that A happened before B. And we also know, since we have seen B here, then we know that A has happened. So that means that once more, x is going to get the value 1, and we're going to try to print the 1. So what about Decker's algorithm? Now it's getting a little more complicated. So can we guarantee that at most one of these two threads can declare success? Which means, can we guarantee that if we perform this this store here, followed by this loading B, so we can make the test, can we guarantee that if that's the order, what assumptions can we make about the order between other kind of transactions here? So given sequential consistency, is it possible that both threads win? And the answer is exactly what Decker wanted. No, it's not possible. So Decker had the kind of sequential consistency in his mind, even though that term wasn't defined yet, when he came up with his algorithm. So how can you prove that Decker's algorithm is correct? So then I'm going to try to do a little hand-waving kind of proof here to show that indeed, if we know its system is sequentially consistent, it's not possible to have an execution where we see b equals 0 here and a equals 0 on that side. That both of them happens and that both sides will print that they want. So here we have it again. So we have stylized the code here. We have a and b equals 0 in the beginning, then we set a to 1, and then we do the test if b equals 0, and on the side we set b equals 1, and then we test if a equals 0. And in this example, we assume that that there is an execution such that both the left side and the right side declare success, and that they say that they did win. And now our job is to prove that that can't happen. So what we do is, once more, we look at value order and we look at program order. So value order is the dashed lines, and program order are the solid lines. And we look at the statement here. So just in program order, we know that store B happens before load A. And we know that store A happens before load B. And since we're going to assume now that this is a execution where left declares success and right declares success, we're going to say that store the value 1 to A in program order happens before load B, where the load B returns the value 0. So we're going to load the value 0. On the right hand side, we're going to store B equals 1. After that, we're going to perform a load operation of A that's going to return the value 0. So if you look at the value order here, you're going to say that this load happened before this store. Likewise, we're going to say that this load happened before that store in value order. So what's wrong with this picture? Well, if this had been a sequentially consistent system, this execution could not have happened, because what you see here is a cyclic order. Okay, there's no defined order here. And that is not okay. So sequential consistency says there is a defined global order between all these transactions. So this proves that this indeed cannot happen. So cyclic access graph means it's not sequentially consistent. If you look at the case where only one of them wins, so now we assume that the right side wins, and they assume that the left side loses, we're going to see this kind of graph. So this load returns a 0 because the right side won, and this load returns a 1 because the left side lost. That puts this kind of value order between the loads and the stores of the different threads. This creates a defined order. It says this store happened before this load, which happened before this store, which happened before this load. It's defined order. There is another value change here, value change order that agrees with us. It says this store happens before that load. So all these observations are in agreement with each other. And so this is certainly something which is possible to execute under sequential consistency. Store B happens before load A happened before store A happened before load B. What about if both of them lose? Is that possible to happen under sequential consistency? Well, remember that Dekker said that's an okay outcome of this algorithm, but would that, if that happens, could we still say that this is a sequentially consistent system? So here I have a situation where both left and right sadly lose this game. So what does that mean? That means that these stores will probably perform pretty much at the same time. And they were so tight in time that this store was observed by this load. So there's this load over here returned 1, and this store here snuck in, and it managed to be observed by this load over here. So it also returns 1. So do we have a cyclic graph here? No, we don't. There is no cycle. We have these two arrows and here, these two arrows and here. So it's not cyclic, and what we will observe here are 4 partial orders. If this store A happens before load B, that's 1. Store B happens before load B, yeah. Store A happens before load A, yes. And store B happens before load A. And there is no contradiction here. So all these different orders are okay. So even if we get partial orders, we can't establish the global order between all 4 different memories. operations, but that's okay. Uh, Lamport doesn't require that. It doesn't require that we can establish the order. It's just that it executes as if there was a global order. We can still define lots of global orders where all these partial orders hold. And that's all which is required by sequential consistency. So in summary, we talked about memory models. Which is a some kind of consistency property or ordering property that defines order between all the loads and stores in the system somehow. It defines what we can rely on based that if we in software have established one order, it can be assumed that everybody else has seen the same order. Sequential consistency gives the illusion of one global order between all memory accesses. If two different threads can observe contradictive orders, even if they are partial orders. So one says B happened before A, the other one says A happened before B. Okay, then sequential consistency is broken. It really maintains human intuition. It really maintains Decker's intuition, my intuition, I assume many of your intuition as well, how a shared memory system should work. But it comes at the cost of complexity, because sometimes we have to force serialization to happen, and that means we have to slow down some memory accesses that otherwise could have been sent out in the memory system. You can potentially get good performance with sequential consistency as well. That requires a very, very complex speculative implementation.